Hello everyone, my name is Alexandra. I am an undergraduate mechanical engineering student from the University of Western Macedonia in Greece, and today I'm going to present you a research with title A Generalized Chaotic Neural Network Model for Epilepsy using Soboleva Hyperbolic Tangent Functions. Let's begin with what is epilepsy. Epilepsy is a neurological disorder where the brain experiences repeated seizures. This happens because of unusual electrical activity in the brain. Basically, it's the imbalance between the excitatory and inhibitory signals. Aside from medical treatments, epilepsy can also be studied as a dynamical system. In other words, we can use mathematical models to simulate how the brain behaves during normal and epileptic states. A healthy brain activity is chaotic, while during seizures is periodic. Now let's talk about chaos and neural networks. Chaos means that small changes in the initial condition can lead to big differences in outcome. We see chaos in many physical and biological systems, including the brain. The artificial neural networks can simulate this complex neurological system, and each activation function decides how the neuron reacts to input. Obviously, modifying the activation function, we can influence its dynamic behavior. The most basic activation function is the hyperbolic tangent or tanh. It's very commonly used because it's smooth, it's symmetrical around 0, and its output is between -1 and +1. But it has limitation when we want to simulate complex behavior. That's where the Soboleva hyperbolic tangent comes in. It's a modified version of tanh and it introduces four new parameters A, B, C, and D. So basically, it adds 4 degrees of freedom and thus greater flexibility. Obviously, when A is equal to B, C, D equal to 1, Soboleva becomes the standard tanh. Here we can see that the parameters A and C affect the right side of the curve, while the B and D the left side. Here is the original epilepsy model. It uses tanh as an activation function. The inhibitory parameter is A, while the excitatory is the B. And here is the modified model. And basically, we replaced all tanh with the Soboleva. To understand how the system behaves under different conditions, we did bifurcation analysis with focus on the parameters A4 and B4. In the original model, we saw some basic and typical chaotic behavior. For example, crisis phenomena, some jumps, and the same behavior in the parameter before. Here the system settles into a periodic state with period 2. Again, crisis phenomena, jumps. And in the new model, using Soboleva, we saw much richer dynamics. For example, when we have this parameter value, chaos is dominant. In this case, we have period 2. In this value, we have a sudden transition between periodicity and chaos. And with changing before, the model also reacts strongly. In this parameter value, we have period doublings. In this case, we have again crisis phenomena. And here the system transitions from chaos to period 2. All this show that the modified model is very, very sensitive to both inhibitory and excitatory changes. Lastly, we looked at the Lyapunov exponents. It's a mathematical way to measure chaos. Positive Lyapunov values mean chaos, while 0 means periodic behavior. In this simulation, we can see that with Soboleva function, the system has dense transition between chaos and periodicity. The black areas indicates that we have periodicity, and with the colors, we have chaos. So yeah, basically we can see that the system is very, very sensitive um, to the inhibitory and excitatory parameters. And this is a good thing because in this way we can mimic the brain's transition more effectively. To sum up, by using the Soboleva function, we add flexibility to the model. And in this way, not only we can create more richer dynamics, but also more realistic ones. In the future, we plan to investigate the effects of the other Soboleva parameters, also analyze more Lyapunov exponents, and lastly, try different activation functions. Thank you for your attention.